This is Ashique Mowla. I am a new PG student here at UTA. The title of the poster I am going to present today is Investigation of Flow Features and Resulting Scour Hole Geometry Around Cylindrical Piers Subject to Wave and Current. The main objective of this study was to investigate the flow characteristics around cylindrical piers and the resulting scour hole geometry. As we can see here, there are more than 20,000 bridges, which means one out of 34 bridges in US are classified as scour critical. That's why there are tons of research on scour. Characteristics of this scour is different under different flow conditions. Primarily, there are three most common flow conditions that can be observed around bridges: riverine or current-alone flow when the flow is unidirectional, coastal or waves-alone flow, and finally lacustrine or wave-current combined flow. Interesting thing is most of the existing studies on scour focuses on bridges under riverine or coastal flow condition. In this figure, we can see the typical flow features in a current-alone flow condition, which includes surface rollers, horseshoe vortex, wave vortex, etc. This figure represents the coastal flow condition, which where only wake vortices are observed. But in a lacustrine environment, combination of both is observed, making the flow much more complex. Another challenge in this area is to collect the data on these major flow features. In this research, a comparative study on the difference in scour pattern under different flow conditions was done. And to do that, I implemented approaches. The first setup included a sandbed section in the middle of the laboratory flume, where all the tests were run. And in the second setup, it employed a PIV or particle image velocimetry setup, which is this one, to investigate flow features around bridge piers. The goal was to prove that the scoured hole is the footprint of the vortices formed around piers. This PIV is a comparatively newer tool and to the author's knowledge never been used to investigate flows involving wave actions. If this approach can be proved as an efficient one, collecting data on flow features which are the causes of scour and eventually bridge failure will become much easier. The sediment bed in the study was designed in such a way that other than the secondary flow near the cylindrical pier could not move the sand from the sediment bed and therefore maintain a clear water flow condition. We can see the dimension of sediment bed over here. We can see different parameters of the sand over here. Also, what equipment we used to build the PIV system. The specifications mentioned here ensured that whenever laser was shoot into the test section, it illuminated the seeding particles. Filming the movement of those particles with high velocity GoPro camera helped us to investigate the flow feature around pier in different flow conditions. A total of 30 experiments were carried out in two sets, 19 with the sediment bed and 19 without the sediment bed. Table 1 here summarizes the test conditions of all 19 experiments performed for each setup. Here I would like to introduce the Kelugan-Carpenter number, which is shown here. Um, this number is the most important factor in characterizing flows involving wave actions. From this results section over here, we can see that when Kc was less than 6, only flow separation happened, which shows the A, B, and C figures. But when the Kc was bigger than 6, partially formed vortices and a twin horn shaped scour hole was observed. These observed pattern can be validated by this study cited over here. In the current alone cases, fully developed vortices were observed, which we can see in this figure. With increasing flow velocity, strength of vortices increased. From the time average velocity distribution, we can see that the flow velocity is very close to zero immediately upstream of the pier and negative at the downstream of the pier. Since there is a stagnation point where the flow meets structure, that justifies the velocity close to zero. Because of the swirling motion of the vortices, negative velocity is observed downstream of the pier. In this condition, the scour hole was inverted truncated cone shaped, which we can see in this figure, and the downstream deposition was roughly trapezoidal shaped. A similar figure can be observed for combined wave current cases, and it shows that this flow was current dominated. Along with this direction of flow, this PIV images also supports that claim. But the effect of wave was also significant, and that can be proved by the fact that downstream deposition transported much further than in the current alone cases. The waves helped to lift the sediment particles from the bed, and the current carried them away. Not just that, flow movement opposite of current direction was identified in these PIV images. From this study, we could indeed prove that the scour hole is the footprint of vortices formed around piers, and PIV can be used to investigate this vortex characteristics in different flow conditions. That was all about this presentation. Thank you.